Welcome to the final part of our series. So far, we've traveled through Rome, Egypt, the Indus Valley, Great Zimbabwe, Angkor, and the Inca Empire. 6 civilizations that mastered engineering with stone, water, and sheer human ingenuity. Today, we're closing things out in China and the Islamic Golden Age, 2 civilizations whose engineers didn't just solve local problems, they built systems and devices that quietly traveled the world and shaped how we build things today. This is a long one, so let's finish the story properly. In 256 BCE, a Chinese engineer named Li Bing was given a serious problem. The Min River kept flooding the Chengdu Plain, destroying farmland year after year. His solution, the Dujiangyan irrigation system, is still functioning today, over 2,200 years later. Instead of blocking the river with a dam, Li Bing's design split its flow using a carefully shaped levee called the fish mouth, diverting a controlled portion into irrigation channels while letting the rest continue downstream, with a spillway called the flying sand weir that automatically released excess water and sediment during flood season, preventing the irrigation channels from silting up over time. To cut the channel through solid rock at Yuli Mountain without explosives, Li Bing's workers reportedly used a technique of heating the rock with large fires and then dousing it with cold water, causing it to crack and fracture along stress lines. The same basic thermal shock principle we saw Great Zimbabwe's builders using half a world away. No computer modeling, no steel gates, just a deep understanding of fluid dynamics through careful incremental testing, refined over generations by his successors after his death, and maintained continuously through an annual desilting ritual still performed by local officials today. Then there's the Grand Canal, the longest artificial river system in the world, with sections built as early as the 5th century BCE and massively expanded under the Sui dynasty around 605 CE, reportedly using millions of conscripted laborers. Eventually stretching over 1,700 kilometers, it connected the Yellow River and Yangtze systems for moving grain and goods, and required engineering solutions like pound locks, chambers with gates at each end that raised and lowered boats between different water levels, centuries before similar technology appeared in Europe. Song Dynasty engineer Qiao Weiwei is credited with refining the pound lock design in the 10th century, replacing earlier single-gate flash locks, which released a sudden surge of water that could damage boats and waste enormous amounts of water, with a safer double-gate chamber system that dramatically reduced both water loss and boat damage. Chinese engineers also developed remarkable technology for detecting and tracking natural disasters. Around 132 CE, the polymath Zhang Heng invented a bronze seismoscope shaped like a wine jar, ringed by 8 dragon heads, each holding a small ball, with a sensitive internal pendulum mechanism that, when tremors reached the device, would trigger a lever causing a ball to drop from the dragon head pointing toward the earthquake's direction into the mouth of a bronze toad below. Reportedly, on at least one occasion, detecting a distant earthquake days before messengers on horseback confirmed it had happened. A genuinely remarkable feat of applied mechanics for the 2nd century. Centuries later, in 1088 CE, the polymath and official Su Song built an enormous astronomical clock tower nearly 12 meters tall in Kaifeng, powered by a water-driven escapement mechanism, a mechanical linkage that released energy in small regular increments, predating similar escapement mechanisms in European clockmaking by roughly 2 centuries, and driving both a rotating armillary sphere for tracking celestial positions, and a series of mechanical figures that emerged through doors to mark the hours. China's engineers also tackled extreme depth. By the Song Dynasty, salt producers in the Sichuan Basin were drilling brine wells using a percussion drilling technique, repeatedly raising and dropping a heavy iron drill bit on a bamboo cable to bore through rock. Reaching depths of over 1,000 meters by the 12th century, a drilling depth not matched in the West until the mid-19th century. Bamboo pipelines, sealed with a mixture including tung oil, carried both brine and naturally occurring natural gas up from these wells, with the gas itself piped directly to furnaces and used to evaporate the brine into usable salt, making this arguably the world's earliest known natural gas extraction and utility pipeline system. And of course, there's the Great Wall, though it's really a patchwork of walls built and rebuilt across more than 2,000 years by different dynasties, using dramatically different techniques depending on the terrain and available materials. Earlier sections, built during the Qin dynasty around 220 BCE under the first emperor Qin Shi Huang, relied on rammed earth construction, where damp earth was compacted in layers between wooden forms, while the more famous stone and brick sections most visitors picture today were largely built during the Ming dynasty, starting in the 14th century using kiln-fired bricks bound with a mortar made partly from sticky rice flour mixed with slaked lime, which modern chemical analysis has shown created an unusually strong, durable bond, contributing to why some Ming-era sections have survived far better than earlier rammed earth stretches. The wall's design also incorporated a functioning communication network. Watchtowers spaced at intervals could relay warnings across vast distances using smoke signals by day and fire beacons by night, reportedly capable of transmitting a warning of an approaching force across hundreds of kilometers of wall in a matter of hours. Chinese engineers were also pioneers of iron chain suspension bridges, a technology that wouldn't reach Europe in comparable form for centuries. The Luding Bridge across the Dadu River, built in 1706 under the Qing dynasty, used 13 massive hand-forged iron chains anchored into stone abutments on either bank, with wooden planks laid across them to form the deck, a design directly descended from earlier Chinese iron chain bridges dating back to at least the Han dynasty, requiring blacksmiths to forge and link enormous chain lengths strong enough to support their own weight across a wide, fast-moving river gorge. Even Chinese manufacturing itself showed advanced engineering thinking. The famous terracotta army buried around 210 BCE to guard the tomb of Qin Shi Huang, China's first emperor, wasn't simply thousands of individually hand-carved statues. Analysis of the roughly 8,000 figures shows workshops used a modular, semi-standardized production system, assembling bodies from a limited set of mass-produced torso, arm, and leg molds, then customizing each figure's head, hairstyle, and facial features individually. It's an early example of what modern manufacturing calls mass customization, standardizing the parts that don't need to be unique while hand-finishing the parts that do, applied at a scale of thousands of units, roughly 2,000 years before the concept became central to industrial manufacturing. Perhaps the most quietly astonishing piece of Chinese engineering still standing today is the Jiaozhou Bridge, built around 605 CE by an engineer named Li Chun during the Sui dynasty. It's the world's oldest surviving open spandrel stone segmental arch bridge, meaning instead of using a full semicircular arch like Roman bridges, Li Chun's design used a flatter arch spanning 37 meters, with two smaller open arches built into the spandrels, the solid triangular sections above the main arch on each side. This reduced the bridge's overall weight, cut material costs, let floodwater pass through more easily during high water, and reduced stress on the foundations, a design so structurally efficient that European engineers wouldn't adopt comparable segmental arch bridges for another 7 centuries. Remarkably, the Jiaozhou Bridge has survived numerous major earthquakes over its 1,400-year history and still carries pedestrian traffic today. Between roughly the 8th and 13th centuries, scholars and engineers across the Islamic world, from Baghdad to Cordoba, made engineering leaps that quietly shaped the modern world. The Persian Qanat, an underground channel using gravity to move groundwater from mountain aquifers to dry farmland, prevented evaporation in the harsh desert climate. Some of these systems still used today in Iran were massively refined and spread during this era, with some individual qanats stretching over 70 kilometers underground and featuring regularly spaced vertical shafts, originally used for construction access and ventilation, still visible today as lines of small craters across the desert landscape from above. In Baghdad, the House of Wisdom, established under the Abbasid Caliphate around the early 9th century, became a center translating and expanding on Greek, Persian, and Indian engineering and mathematical texts, drawing scholars from across the known world. One of the earliest engineering breakthroughs to emerge from this environment came from the Banu Musa brothers, 3 siblings working in Baghdad in the 9th century, whose book of ingenious devices documented around 100 mechanical inventions, including early self-trimming oil lamps, automatic fountains with alternating jet patterns, and one of the first documented designs for a simple mechanical valve system for controlling gas and liquid flow. Building on that tradition roughly 3 centuries later, the engineer Al-Jazari, working in the 12th and 13th centuries for the rulers of Diyarbakir in what's now southeastern Turkey, documented dozens of further mechanical inventions in his own book of knowledge of ingenious mechanical devices. Beyond crank-driven water pumps and programmable automated machines, Al-Jazari also designed elaborate water clocks that used calibrated floats and precisely metered flow rates to track time with remarkable accuracy, and described a design for a segmental gear system centuries before similar gearing reappeared in European mechanical clocks. His famous elephant clock combined Indian, Persian, Greek, Chinese, and Arab design elements into a single working timepiece, deliberately built as a symbol of how interconnected the engineering knowledge of the era truly was. Windmills, first clearly documented in 9th century Persia, used vertical sails rotating around a central vertical axis to grind grain and pump water. A design suited to the strong, steady winds funneling through the region's mountain passes, which later evolved into the horizontal sail windmill design most people picture today. After the underlying concept spread toward Europe over the following centuries, Andalusian engineers in southern Spain built extensive networks of acequias, gravity-fed irrigation channels adapted from earlier Roman and local Iberian techniques and refined further using Middle Eastern water management knowledge, which transformed arid regions into some of medieval Europe's most productive farmland. Some of these channels are still in active agricultural use in parts of Spain today, essentially unchanged en route from their medieval construction. Meanwhile, in Hama, in modern Syria, engineers built enormous wooden noriyas, water wheels up to 20 meters in diameter, powered entirely by the natural current of the Orontes River, lifting water in attached clay pots up to elevated stone aqueducts that then carried it across the city and out to surrounding farmland. Several of these noriyas remarkably still stand and can still turn today, nearly 1,000 years after the oldest surviving examples were built. In Cairo, engineers built similar animal-powered chain and pot mechanisms called sakiyas, using a geared wheel turned by oxen or donkeys to lift water from the Nile to elevated distribution points, allowing irrigation across land that natural flooding couldn't reach on its own. Islamic engineers also left a lasting mark on architecture through structural innovation. The Great Mosque of Cordoba, begun in 785 CE, used a distinctive system of double-tiered horseshoe arches, stacking one arch on top of another using alternating red brick and white stone voussoirs, which allowed the building's roof to reach far greater heights on relatively slender supporting columns than a single tier of arches could safely achieve, a structural solution that influenced mosque and cathedral architecture across the region for centuries afterward. Scientific instrumentation advanced alongside mechanical engineering, too. Working in Cairo in the early 11th century, the scholar Ibn al-Haytham conducted detailed experiments using a camera obscura, a darkened chamber with a small aperture that projects an inverted image of the outside world onto an interior surface, to study how light travels in straight lines, laying groundwork that later influenced the design of optical instruments and, eventually, the camera itself. And in the 16th century, at the tail end of this broader tradition of Islamic mechanical engineering, the Ottoman engineer Taqi al-Din described a 6-cylinder piston pump for raising water and, separately, a basic device using steam to rotate a wheel. A rudimentary steam turbine concept developed and documented roughly 2 centuries before Western steam engines became practical, though it never advanced beyond a working demonstration. Manufacturing knowledge spread through this network too. Papermaking, originally developed in Han Dynasty China, reached the Islamic world after the Battle of Talas in 751 CEE, and by 794 CEE, Baghdad was home to a fully operational paper mill using techniques adapted and improved along the way, including large-scale use of water-powered pulping mills, replacing hand-pounding with mechanical hammers driven by flowing water, dramatically increasing production speed. This cheaper, faster paper production directly enabled the House of Wisdom's translation projects and the broader documentation of engineering and scientific knowledge that defined the era, centuries before paper mills appeared in Europe. Separately, in 9th century Cordoba, the inventor Abbas ibn Firnas is credited with one of history's earliest documented attempts at human flight, constructing a glider-like apparatus of silk and feathers and reportedly gliding a meaningful distance before a rough landing. An early, if imperfect, application of aerodynamic thinking centuries before any formal theory of flight existed. In Muslim Spain, engineers extended this same water management expertise into palace design. At the Alhambra in Granada, built primarily under the Nasrid dynasty starting in the 13th century, engineers channeled water from the Darro River through a hillside aqueduct system into the palace complex, powering an intricate network of fountains, reflecting pools and channels running directly through courtyards and garden walkways, purely through gravity-fed pressure, with no pumps timed and routed precisely enough to keep water audibly flowing through certain rooms, as a deliberate architectural and acoustic effect. These weren't isolated inventions. They were part of an interconnected exchange of ideas across trade routes stretching from Spain to China, with paper-making knowledge, mathematical concepts, and mechanical designs moving in both directions along the Silk Road and Islamic trade networks alike, proving engineering progress has almost never happened in a single place. It's always been a global relay race, with each civilization picking up the baton, refining what came before, and passing it along further than the last. What ties all 8 of these civilizations together isn't steel, steam, or electricity. It's observation, patience, and an intimate understanding of the materials and environment around them. The engineers of Rome, Egypt, the Indus Valley, Great Zimbabwe, Angkor, the Inca Empire, China, and the Islamic Golden Age didn't have the Industrial Revolution's tools, but they had something just as valuable: an obsessive drive to solve real problems with whatever they had on hand. tested and refined over generations rather than invented overnight. The Industrial Revolution didn't invent engineering. It just gave humanity a louder, faster set of tools to keep doing what we'd already been doing brilliantly for thousands of years. That wraps up our three-part journey through the forgotten engineers who built our world long before the first factory ever opened. Thanks so much for watching the whole series. If you enjoyed it, leave a like and subscribe so you don't miss what we dig into next. See you in the next one.